right, so we're just going to continue the titration calculations. The next point that we're going to be interested in is the equivalence point. And so let's go ahead and do that. So we did the buffer region. As we get close to the equivalence point, we'll have to actually, let me talk about the buffer region a little bit more here. As we get close to the equivalence point, we start to worry about the mixture. Let's see, twist this. I didn't bring my mouse. We start to worry about it, and so there are a couple of more things I want to say about the buffer region here before moving on. And this is called the buffer region because step 2. In step 2, we're left with excess acid. I call this the excess acid region, and its conjugate base, which would be acetate or sodium acetate. And the buffers are stable mixtures containing both acid and base. So, for example, here we have our acetic acid, which is acid, but acetate is non-neutral. Acetate is a base. And they're both present. They're both present because they don't neutralize each other. So for example, if I have acetic acid plus acetate and tried to come up with a reaction, the most likely reaction between these will just form acetate and acetic acid, which is the same thing. So it's going to mean it's a stable mixture. Although, some will react with water. And so here we're going to have the Ka for acetic acid and the Kb for acetate. Depends on which one's stronger. So for example, here the Ka for acetic acid is bigger than the Kb for acetate. And as the Ka is bigger, then it's a stable mixture, but it's not neutral. It's not neutral because the Ka is going to produce more hydronium than the Kb will produce hydroxide. And so this one turns out to be acidic. It depends on the acid-base combination. Some acid-base combinations will result in an acidic buffer, some will result in close to a neutral buffer, and some will result in a basic buffer. Depends on what's bigger. But it gives the buffers interesting properties. One of the interesting properties of buffers is its ability to maintain a stable pH. And the way we do this is, for example, if we take a buffer, like here, we're in the flat part, and we add a strong acid. Normally a strong acid results in a significant drop in pH. But here, if we add a strong acid, what we see is just a small drop in the pH. It's a small drop in the pH because strong acid will attack the base component here, but when it attacks the base component, it just makes conjugate acid. The conjugate acid is weak. As long as the strong acid is not in excess. If the strong acid is not in excess, then the strong acid is neutralized by the base, and we generate some more HAC, which changes the ratio a little bit. And that change in the ratio just results in a small change in pH, so it goes back down. So we could kind of go in the reverse. If we add strong base, it remains fairly flat. It remains fairly flat because what happens with a strong base is it's going to neutralize our weak acid, resulting in conjugate base. So it just changes the ratio again. So we just have a little bit more base, conjugate base, and it stays flat. So in the buffer region, the pH is relatively flat. However, if this were unbuffered, then we're going to see more significant increases or decreases in the pH. We'll do some calculations to show how significant those changes in pH are. But that's one of the features, and this is why it's so flat in the buffer region. I'm tilted here, so it kind of looks like it's tilted up, but that's because my drawing isn't so good. However, at the extreme edges of the buffer region, do you see the pH changes more significantly? And so what we say is that to be a useful buffer, we don't want it too lopsided. And what I mean by too lopsided is this. And so normally when we think of buffers, we think of the buffer range. And so this is just a side topic. I didn't talk about buffers yet, so I want to talk about it in the context. This is an easy way to make buffers, but there are other ways we can make buffers as well. And so, not neutral. This one's going to be acidic. And so there's an ideal pH for this buffer. You know, if we're going to make a buffer, the ideal pH is when we have a 50-50 mix of acid to base. And this is, we're talking about weak acid, weak base, the conjugates of one another. And so the ideal pH for the HAC, AC minus buffer is when we have equal amounts of acid and base. Equal amounts is just a 50-50 ratio, you know, equal amounts of both. That is, the concentration of the HAC initial is equal to the concentration of AC minus initial. And where does that occur? Well, that occurs at the half equivalence point in this titration. And so this will be at the half equivalence point. And therefore, the ideal pH for this buffer is equal to 4.744. That's ideal. And so if we have a pKa table, then we can see. Let's just take a look at a pKa table here. Do this. Or we could do it based on Ka2 values. But if we have a pKa table, then it's a little easier to see from this. Come on. Let me just grab one off the internet here. This is free. Let's see. This is free. DMSO. Haven't heard of that in a while. Here's a pKa table for. Oh. Oh, this is a pKa table for organics. If you look at hydrocarbons, take a look at the pKa. pKa is about 50. 50, which means the K is extremely small, 10 to the negative 50, which means alkanes aren't very acidic. So if you look at alkanes, alkenes aren't very acidic. Alkanes are hydrocarbons with all single bonds. Alkenes will have a double bond in there, but still, pKa, a little bit more reactive. The alkenes are probably a little bit easier to deprotonate. Deprotonation is something that organic chemists are very interested in, because if you could deprotonate your hydrocarbon, then you created a very reactive species, a radical, and then you can make new things. Organic chemistry, it's very rich, the chemistry is, and you can make new compounds. New compounds are being synthesized all the time in organic chemistry, whereas in inorganic chemistry, organic chemistry focuses on carbon. Carbon has a lot of bonding possibilities. And therefore it forms lots of molecules, lots of different kinds of compounds. So that's why it's divided into a whole separate category. You can see out of all these, the alcohols here are the most acidic, but pK of 16 is like not acidic at all. So we don't really consider alcohols acidic, unless it's phenol. Phenol has a pKa around 10, which makes it quite a bit more acidic than the other alcohols are like a million times more acidic. Water is 14. We're using 14 for the pKa of water. pKa of water is the same thing as pKb of water, which is the same thing as pKw of water. Here's a carboxylic, or this is an ester. Oh, here's phenol. Phenol is unusual in its acidity. Yeah. Here's some amines. Oh, not amines, ammoniums. Ammoniums are fairly acidic as well. But, if we use, let's see, hydrochloric acid. Hydrochloric acid pKa of minus 7. Carboxylic acid. So for carboxylic acids, we can make buffers around pH 5. Those are pretty good. If we look at some bases, then we can make things with higher pHs, lower pHs. But for something like hydrochloric acid, can we make a buffer in the -7 pH range? No, because remember, a buffer is a weak acid and a weak base combo. If you look at hydrochloric acid and sodium chloride, it's not a buffer. It's not a buffer because sodium chloride is not going to neutralize anything. It's a neutral salt. So it would have to be weak on both ends. And so strong acids are buffers, and so we aren't going to make a buffer out of that, and so it wouldn't be relevant. And normally what we say is that these are, the pKa's are so small that the K's are so big that we just call it very large. Check out this acid though, trifluic acid. Trifluic acid is the strongest acid on this, and it's like 4 orders of magnitude stronger than hydroiodic acid. It's just not very common, this trifluic acid. So it's this sulfur. It's this sulfur and this if we have CF3, what do you automatically recognize of a CF3 group? This looks like sulfuric acid, kind of. Sulfuric acid would have another OH here. But now we have a CF3. What does a CF3 do? What type of group is that? It's what we call electron withdrawal. It's a heavy electron withdrawal of the fluorines and stuff. This wasn't the table that I kind of wanted. Let's see, there's a better pKa table. This would be a better pKa table here. So, something like carbonic acid. We use carbonic acid, its pKa is around 635. Optimum pH for this buffer. It would be carbonic acid bicarbonate buffer. Actually, carbonic acid bicarbonate buffer is what helps your blood maintain a more stable pH. You know, your blood pH isn't 635, your blood pH is higher, above 7. But you have two buffers in your blood, carbonic acid bicarbonate and dihydrogen phosphate, I think. And monohydrogen phosphate. I got boric acid, 9. So boric acid would be, you know, in the higher pH range, 9.15. So if we're looking at boric acid, we're looking at boric acid as the acid and dihydrogen borate as the base. Benzoic acid and benzoate would be around there. Here's our 4. I have 474, 4, you know, but they're using a Ka value of 1.7 times 10 to the minus 5. Our book has a Ka value of 1.8 times 10 to the minus 5, so which one's more accurate? You know, where would we look, you know, to get the latest information? What book would we look at, or website, if you have a subscription? Don't remember? It's got a funny name, the CRC, the Chemical Rubber and Company. It's a CRC Handbook of Chemistry and Physics. Is a pretty good source to look, because if I see a conflict like this, then I'd want to get the latest data. And so that's why they got a 475, they got a 474. But looking at this, ooh, this looks pretty good. This has actually if you look at hydrogen sulfide on our chart here is 1 times 10 to the negative 7. And they have hydrogen sulfide is 8.9 times 10 to the minus 8. I wonder how recent this data is. Oh, no, this is 9.1. 9.1 times 10 to the minus 8. This is not recent. Our book is 1 times 10 to the negative 7. So our book has more recent data than that. But I wonder if this is old or new. Well, anyway, it's very close to 7. And so this would make a nice pH 7 buffer, except the problem with the H2S is it's normally gas, and it smells very bad. And there's two other problems with it. Not only does it smell very bad, it's very toxic. And the other problem is it has very limited solubility in water. The maximum amount that you can dissolve of H2S in water is only 0.1 molar. That's the max. Because there's another thing that we worry about when we make buffers. The other thing we worry about is buffer capacity. The buffer capacity is, you know, how much acid, how much base is actually contained in your solution. Because remember, solution dilution shouldn't impact your pH up to a certain point. And so what happens is, let's say you buy some buffer and you dilute it. You buy some buffer, you dilute it, it's the same pH. So when you buy buffers, you know, the cost is going to depend on how dilute it is. The more dilute, the cheaper it is. But the more dilute it is, the lower the capacity of withstanding changes is, because you could soon overwhelm your buffer. Let's say you add so much acid in there, it completely wipes out the base component. When it completely wipes out the base component, then your pH changes dramatically, because you go from a buffer solution in step 2 to a strong acid, weak acid mixture. And so, but these are all pKa values we can use to determine it. Well, let's say I don't want a buffer 474. If you don't want a buffer at 474, let's say I wanted a buffer at 4.00, then that's not a problem. All I have to do is increase the amount of acid relative to the base. And so I have more acid than base, that's going to drop the pH. But I can only do that to a certain limit. So we have something called the buffer range. And so this is, I'm just going to continue on this side topic. But this is important. This is not a side topic. This is a major topic. And so the next thing we look at is buffer range. Oops. In other words, the buffer range is the pKa plus or minus 1. The buffer range, the reason we call it is because we need it not too lopsided. So for example, if we're at a pKa minus 1, then we have 10 parts more acid than base. And so if we look at the base to acid ratio, it's a 1 to 10 ratio. If we go to pKa minus 2, then we're at a 1 to 100 ratio. If we go to pKa minus 3, we're at a 1 to 1,000 ratio. And so what we want to do is we want to keep it within a 1 to 10 up to a, well, pKa, if we're looking at just pKa, then it's a 1 to 1 ratio. If we're looking at pKa plus 1, then we're looking at a 10 to 1 ratio. If we're looking at a pKa plus 2, what are we looking at? This is the pH. A pKa plus 2 means a 100 to 1 ratio. This would be pKa plus 2. And so the buffer range is to have a reasonable base to acid ratio. What is a reasonable ratio? A reasonable ratio would be between 1 and 10 and 10 to 1. This is a reasonable ratio. Whereas this would be a lopsided ratio. It's can I make 1,000 molar? Can I make 1,000 molar acetic acid? That's impossible. Pure acetic acid is way less than 1,000 molar. That's pure acetic acid. It's impossible. So in order to get a 1,000 to 1 ratio, we make a 1 molar acetic acid, but the acetate is going to be 0.001 molar. 0.001 molar, 1 millimolar is not enough. Can barely neutralize anything. And so this is reasonable. This is lopsided. And so what we had in ours, we just, when we made our pH 4 buffer, we just went down pKa minus 0.74. So we're at pKa here right in the center, and we just went minus 0.74, and then we made our pH 4 buffer here. So it wasn't too lopsided. The next thing we worry about is buffer capacity. You know, this is like if you go buy a 1 gallon tank of helium, right, what would you want to know? If you go buy 1 gallon, so you bought 1 gallon of helium, but do you want to buy helium by the gallon? Somebody gives you a 1 gallon sized balloon of helium, right? Are you going to be able to fill any other balloons from that one balloon? No. Somebody gives you an empty or nearly empty tank of helium. And so when we buy helium, we want to know how many grams of helium are actually in that tank. You know, because 1 gallon is totally meaningless. because gases can expand or be compressed, or we would not want to know what the pressure in the tank is. If the pressure is just room pressure, then it's empty, essentially. If it's 2,000 psi, then we have lots of helium in there. So usually when we buy helium, it's a fresh tank of helium is 2,000 plus psi helium in there. Or we buy it by the gram. Usually we buy it by the gram. The same thing with buffers. If you buy a cheap buffer, it's going to be very dilute, to concentrated. The more concentrated, the higher the capacity. The more dilute, we have the lower capacity. So of course we want, and it'll be the same pH because it just depends on the ratio. So if you buy a pH 7 buffer, you don't know what the capacity is. It could be a high capacity buffer or low capacity buffer. So buffer capacity is important here. So when we're looking at the buffer region in the titration curve, the buffer region in the titration curve extends from, to make an optimum buffer, we go from the 1/11th, this is why I like the 1/11th and the 10/11ths. What's significant about the 1/11th and the 10/11ths equivalence point? When I see 1/11th equivalence point, then what's my base to acid ratio? When I see my 1/11th equivalence point, then the base to acid ratio is 1/11th over 1/11th has been neutralized over how much acid remains unneutralized. 10/11ths. A 1/11th equivalence point is a 1 to 10 ratio of base to acid. The 10/11ths equivalence point, what's the base to acid ratio here? Well, I neutralized 10/11ths of my acid that produces 10/11ths base, and how much do I have left over unneutralized? 1/11th. And so this gives me a 10 to 1 ratio of base to acid. And so this would be the buffer range, right? Between the 1/11th equivalence point and the 10/11th equivalence point, that's what we call the buffer range. This is the optimum range for maintaining a flat, stable pH. The pH does change. For sure it's not horizontal. That is, the slope is not 0. The pH does change, but it doesn't change much. When you're adding strong base to it, did the pH change much through this range? No, it didn't change. The change was kind of small here. However, what we're going to do is we're going to use the Henderson-Hasselbalch. For the Henderson-Hasselbalch, it doesn't have to be an ideal buffer. We could use the Henderson-Hasselbalch equation in a lopsided buffer. The only thing that has to happen with the Henderson-Hasselbalch is what? What assumption do we make in using the Henderson-Hasselbalch equation? The SA has to work. The SA works beyond this ideal buffer range. This is the ideal buffer range. And so for Henderson-Hasselbalch, we extend it beyond this. So for Henderson-Hasselbalch, I use this almost to the very beginning here and go wider. And so let me outline that here. So for Henderson-Hasselbalch, I use it nearly to the ends here. And so use the HH equation well beyond the 1/11th and the 10/11ths. So the HH equation. I'm going to use practically to the very ends. However, when I get very close to the end, then I have so little of one component that I shouldn't use the Henderson-Hasselbalch because the SA will fail. when the concentration becomes so low here. And so then this green region here at the very extremes, I would have to use ice at the very extremes. Okay, but you can see how the pH is kind of stable in the buffer region, and this is what people use buffers for. People use buffers to maintain a stable pH. You add some acid, you add some base, the pH doesn't change so much. You dilute it, the pH doesn't change so much. Actually, you dilute it, the pH shouldn't change at all unless you overly dilute it. If you overly dilute it and it becomes like water, then the pH is going to change. Okay, so now we're going to be outside the buffer region here. I'm not going to do a calculation in the green. In the green, you just do regular calculation like you would, step 1, step 2. Step 2, you just do an ice equation instead of the Henderson-Hasselbalch equation. You'll be fine there. What we're going to do is we're going to go on to the next point that we need to calculate, and that's going to be at the equivalence point. At the equivalence point, this is going to be plus 20.00 milliliters of sodium hydroxide solution. That'll neutralize my 20 milliliters of acid because they're the same concentration. And so here I do my step I, which is I'll just take my 20.00 milliliters of acid and add 20 milliliters of base to it. And then altogether, I'm going to have 40 milliliters of solution now, product solution. And then I need to figure out the new concentration of acetic acid. This will be my initial. The new initial concentration of acetic acid is going to be a 20.00 to 40.00 times 0.100 molar. And so this is going to be a 0.0500 molar. This is just a 1 to 2 dilution. And then the sodium hydroxide is going to be the same. It's a 1 to 2 dilution, so this is going to be 0.0500 molar. Since I chose these numbers to make the calculations simpler, you might not have simple numbers. Okay, now we'll go to step 1. Step 1 is strongest acid, acetic acid, plus the strongest base, sodium hydroxide. This is going to make sodium acetate plus water. So my new initial is 0.0500 after solution dilution, and then I'll have 0.0500 and 0. Water is a liquid. And so this is stoichiometric. No limiting, no excess. So this is going to go to 0. This is 0. This is going to be 0.0500. This is not a buffer because we don't have any acid component. But you say, well, acetate. Acetate's a base that hydrolyzes water. Acetate's a base and it hydrolyzes water to form acetic acid. Does that qualify as a buffer? No, it doesn't qualify as a buffer because the amount of acetic acid is too small. We need significant initial concentrations of both. Some people might think this is a buffer because this is acetic acid and sodium hydroxide. This is not a buffer because they have to be conjugates of one another, number one, and one can't be strong. It's not a buffer. And so step 2 is just a basic salt. I'm going to skip the ionization of sodium acetate, and so I'm just going to go straight to acetate. Acetate's the base. And so, in other words, I skipped. Sodium acetate ionizes into sodium ions and acetate ions, like all soluble salts do. They ionize into the ions. However, that's ideal behavior. Ideal behavior is they completely ionize. Okay, so I'm forming acetic acid here, and some people might say, hey, that's a buffer. No, it's not a buffer because I need significant initial concentrations of both. I have significant initial concentration of acetate, but I have 0 initial acetic acid and 0 initial hydroxide. And so this does not qualify as a buffer. The Kb for acetate we have to get. The Kb for acetate is equal to Kw divided by the Ka for its conjugate. What's the conjugate of acetate? The conjugate of acetate is acetic acid. And so this is going to be 1.0 times 10 to the negative 14 divided by the Ka for acetic acid, which is given at 1.8 times 10 to the minus 5. That's what do we have on this table over here for acetic acid? 1.76 times 10 to the minus 5. Our book is 1.8 times 10 to the minus 5. I don't know which one's more accurate. Maybe that 1.76. Oh. So this is why we want, when we're doing science, like if it really matters, I would look this up. But this is a Chem 1B calculation, so I'm not going to bother looking it up. But if you're actually working in the laboratory and you didn't want to waste time, you know, can you imagine doing all your calculations with the wrong value of Ka and then having to go back and redo all your calculations? That would really suck, wouldn't it? This is why you should know where to find the latest sources of data. You know. Or, you know, it would be embarrassing, you know, if you go into a conference and you're talking about your calculations and people notice you're using old data. You know, why aren't you using the latest numbers? Wouldn't that be pretty embarrassing? Maybe. Or maybe you wouldn't care, I don't know. Some people might not care. Or maybe the numbers aren't really sorted. Well, anyway, let's figure out. I'm just going to use 1.8 times 10 to the minus 5 because that's what we have in our book. And I'm going to get 5.55. I'm only allowed 2 sig figs, but I don't like to round too much. You know, people who like to round every step end up having large percent errors, potentially, at the end of their calculation. And so I try to minimize rounding until the very end, then I'll round it at the very end. And so I carry at least 1 extra digit minimum. Sometimes I carry more than 1 extra digit. Depends. But you should get in the habit of carrying 1 extra digit at least to try to minimize round-off error. So the Kb is quite small. It's 10 to the minus 10. Acetate's not that good of a base. But let's go ahead and do the calculation. So this is just a standard Kb calculation like in chapter 17. So that's going to just equal. I'm going to skip the writing the K expression. Let's just go straight to x squared over 0.500 minus x. And then this Kb is so small, I'm sure the SA is going to work nicely here. X squared over 0.500. And so I'll take my Kb times 0.5 and equals, and then take the square root of that. And I get x equals 1.66 times 10 to the minus 5. So this is a judgment call here. 1.66 times 10 to the minus 5 molar hydroxide. Should I worry about Kw? Oops, did I? Yeah, I did. Shoot. Let me fix that. That's going to change it. right, thanks. Let me redo that calculation here. I'll carry some extra 5s because it just kept going. 5s. Times 0.05. And then take the square root of that. 6. Let me try that one more time. Times 10 to the minus 10 times 0.05. Take the square root of that. Okay, I get a different x value now. It's 5.27 times 10 to the minus 6. Okay, well, number one, the percent change is going to be very small. I might as well calculate it. Percent change is this divided by 0.05 times 100. 0.01%. And so the SA was no problem here. But now I have to worry, it's 5.27 times 10 to the minus 6. So the question is, should I worry about hydroxide from water? I mean, it's 10 to the minus 6 is kind of small. But, you know, I'm not going to get 10 to the minus 7 from water because that's only if there was no common ion. Since there's common ion, the common ion effect is going to restrict how much hydroxide I get from water significantly. So if I went ahead and did step on my own, step 3 here, which is just water plus water, excuse me, hydronium plus hydroxide. Because of the common ion effect, 5.27 times 10 to the minus 6 molar to begin with in Le Chatelier's principle, we don't expect much extra. In fact, way less. I mean, if this were 0 and 0, we could get 10 to the minus 7. We're going to get a lot less than 10 to the minus 7. In fact, we're going to get something more on the order of 10 to the minus 8. Well, if it's on 10 to the minus 8, then that could be like 1 out of 100. So it could be like a 1% additional hydroxide. So maybe we should consider it. And so I'm going to go ahead and consider it and see what happens. This is just a guess here. This is going to be plus x molar plus x molar. And so at equilibrium, I'm going to get x molar here and 5.27 times 10 to the minus 6 plus x. Over here. Oh, just lost my parentheses. Save this before. So KW is going to be x times 5.27 times 10 to the minus 6 plus x. And that's equal to 1.0 times 10 to the minus 14, which is extremely small. So I think the SA will work. But one point of confusion that people have is, if the SA works, then why bother doing this step? And so this is something that's kind of weird. Because on the one hand, we say the SA works, so how much hydroxide are we going to get from step 3? None, right? So initially we say, yeah, we're going to get none. And then if we're going to get none, why am I doing this? Why am I doing this step? Does it make sense? Because if the SA works and we're going to get none, then why bother? And then what's your answer? You know, if somebody asks you, why are you doing that? Why are you wasting time? What would you say to them? So you would say that, yeah, we're making the assumption first to try to simplify the math to get the x value, and then we're going to say, no, wait a minute, it is significant, and then we're going to add the x after. And so, yeah, we're going to say it's, and so it's kind of a double standard. And this is just a very common double standard that we do. The common double standard is we say it's negligible, and then we go back and say it's significant. And add it and see, was it really negligible or was it significant? And not only that, we're going to have an error in our calculation. But anyway, let's calculate what our x comes out to. So I have 1 times 10 to the negative 14 times, or divided by 5.27 times 10 minus 6. And I get 1.89 times 10 to the minus 369 times 10 to the minus 9. So it's significant over here. We need to do it because compared to 0. So we're going to have 1.8 times 10 to the minus 9 molar hydronium. And then the hydroxide is, okay, this is 10 to the minus 6, that's 10 to the minus 7, that's 10 to the minus 8 times 10 to the minus 9. So this would be 5.27189 times 10 to the minus 6 molar. So was that a significant change or was that kind of a minor change? This is kind of a minor change because this is going to be rounded off when I do my sig figs. Do you see that? But nonetheless, we're going to do that. And let's do our K check here to make sure we're still in there. So I'll do 1.89 times 10 to the minus 9 times 5.27189 times 10 to the minus 6. And we get 0.996 times 10 to the minus 14. And so this rounds to 1.0 to 2 sig figs times 10 to the minus 14. So we're okay. So doing this step, did it change the pH? Yeah, it changed the pH. Did it change the pH to the point where we would notice it after rounding? No, it didn't. So if we calculate the pH here, let's go ahead. So in this case, there are 2 ways we can do this. One, since I went ahead and calculated the hydronium, I could just go ahead and calculate the pH based on the hydronium concentration. And so I'll do that. I have the log of 1.89 times 10 to the minus 9. And the pH comes out to 8.723. Now, I'm only allowed 2 sig figs. And so rounding this to 2 sig figs, what would it round to? 8.7 or 8.72 to 2 sig figs? 8.72. 8.72 is 2 sig figs. And the reason is anything preceding the decimal is not significant. It's just the, what we call the exponent or exponential term. And so this is 2 sig figs. All right, or I can calculate my pOH. The pOH would be the negative log of the hydroxide. And so let's go ahead and take the log of the hydroxide. And so The hydroxide is 5.27189. 5.27189 times 10 to the minus 6. Let me try that again. That comes out to 5.277. And therefore, the pH is 14 minus that. 8.722. Those are two ways of determining the pH. We could get to the pH via going from the hydronium directly, or we can solve for the pOH and then determine the pH from that. We get the same number. This is, we got 8723, we got 8722. They're the same number within round off. You know, this was round off error is the reason why they're different. But did we need to do step 3? And so if we went back to step 2 and calculated the pOH, so let me go ahead and do that. Based on step 2, we get a pOH of 5.27 times 10 to the minus 6. The log of that. 5.278. So I get a pH of 5.278, which gives me a pH of 8.721. We're allowed 2 sig figs, so this rounds to 8.72. Yes, the pH did change a little bit, but once we round it, it came out the same. 872. And so this added a little bit of, this added 1 part in 1,000. And so this is kind of borderline. So if I have 10 to the minus 6, I probably wouldn't do kW if I'm interested in pH. Does that make sense? If I had 10 to the minus 5, definitely wouldn't do it. If I had 10 to the minus 7, I probably would do it. And so that gives you an idea of the cutoffs. But those cutoffs depend on how big the K, you know. Well, it's a good thing it didn't change much. Because if kW did change the hydroxide significantly, you know what we'd have? We would have to do this, not stepwise, simultaneously. All right, so now we have the pH at the equivalence point. The pH at the equivalent point is not pH 7. And it's not pH 7 because we form not a neutral salt, we form a basic salt. And so this pH comes out to 8.72. That pH is perfect for phenolphthalein. Do you know where phenolphthalein turns pink around? What pH? Phenolphthalein does not turn pink at pH 7. You know where phenolphthalein turns pink around? pH 9. And so this is pretty good. Because the indicator, you know, it would be perfect if phenolphthalein changed color at 872. It doesn't, you know, but it's close. It's close enough. And the close enough is, you know, this is so steep that, you know, if it changes color at pH 9, it's just like less than a drop, you know, away. And so it's a minimal error. It's also a systematic error because we're doing all our titrations using the same indicators. So everything's going to be systematically off, which is kind of cancel things out. Potentially. Okay, the next calculation we're going to go is in the excess base region. The excess base region is just this. So here, you know, very close, kW is going to be the most significant contributor to the hydroxide. We have so little excess sodium hydroxide that kW is the most significant contributor here. However, once we are at high enough pHs over here, then the hydroxide is going to be the main contributor to the sodium hydroxide. The excess sodium hydroxide is going to be the main contributor to the pH. So this is what we'll do. We're going to do maybe 2 calculations in the excess base region. Okay, the first calculation we're going to do is 1 drop after the equivalence point. And so at equivalence point plus 1 drop. 1 drop we're going to estimate as about 0.05 milliliters as 1 drop. There are about 20 drops in a milliliter. And so we'll just, it's about 0.05. So equivalence point plus 1 drop will be plus 20.05 milliliters of NaOH. So let's see what the pH goes up to after 1 drop. So we're adding 20.05 milliliters to our 20 milliliters here. And this is going to give us a total volume of 40.05 milliliters. And then let's go ahead and calculate the concentrations. The numbers are going to come out not so clean here, and I got to carry extra digits. Sort this. So this is going to be a 20 to 40 dilution, but at 40.05 dilution of 0.100 molar. This fraction is called the dilution factor. Dilution factor, people know because it's easy. It's almost a 1 to 2 dilution. And so that fraction is the dilution factor. So it's a 20.05 to 40.00 or 40 dilution of 0.100. And that comes out to 0.050125. This time I'm going to carry extra digits because I'm just adding 1 extra drop. And if I round this, I round off that extra drop, kind of. And so I'm going to go 50125 molar. And then the sodium hydroxide is going to be a 20.05 to 40.05 dilution of 0.1 100 molar. And so 20.05 to 40.05 dilution of 0.1 gives me a concentration of 0.500. Uh-huh. Oh, yeah, you're right. It's got to be lower than 0.5. Sorry. Let me fix that. 0.4. I must have had it flipped. 499. What? 375. Okay. 0.04. Sorry, screwed it up again. 0.04. Where am I coming up with these numbers? I should use, well, let's do the second one. 20.05 divided by 40.05 times 0.1. Okay, this one comes out to 0.0500. I'm just gonna, maybe I'll carry 3 extra. I'll carry 3 extra. That should minimize the round-off error here. So I'm carrying 3 extra here. I'll carry 3 extra here. I don't want to carry all of them in my calculator, otherwise it's too much. 1 extra is a significant improvement in round-off. 2 extra is better, for sure, but not hugely. 3 extra is no difference. So if we go 2 extra versus 3 extra, it's not a very big difference. But since we're only talking about 1 drop, I'm going to go 3 extra. So that's my step I. And then I'll do my step 1 here, which is going to be the HAC plus the sodium hydroxide. This is going to yield sodium acetate plus water. The HAC is 0.0499375. Your book loves to use milli. I could use milli too. So for example, if we convert this to millimolar, what would it be in terms of millimolar? In terms of millimolar, it would be 49. You know, just move the decimal point over. So 49.9 millimolar. This would be 50.0. But if I do millimolar, I'm going to have to switch back to molar anyway, so I'm not going to bother doing millimolar. I'm just going to leave it, you know, and hassle with the decimal points. So this is going to be 0.0499375 molar. And the sodium hydroxide is going to be excess, 0.0500624. But it's only one drop excess, and then this is going to be 0. And so the limiting reagent here is going to be what? The acid. We've neutralized all the acid. So the acid is going to go to 0. And this is going to be minus 0.0499375. And this is going to be plus 0.0499375. And so this one's easy, 0.0499375. And then over here, what are you going to get for this? So 0.05 minus 0.0499375. 000. So I'm going to get 0.0001249. Okay, that should be good now. So what type of solution is this? This is what we call a strong base, weak base mixture. Strong base, weak base mix. So in other words, it's a mixture of bases. This is a mixture of bases. We want to go with the biggest KB first, right? And so your book is going to skip these steps. I usually, you know, you can always do shortcuts. Like for example, I did this shortcut earlier, you know. We call sodium hydroxide a soluble salt. And so it's going to complete, you know, this is going to be complete. And so how much hydroxide am I going to get from this? I'm going to get 0.0001249 molar here. That's complete. Sodium salts are all soluble, so I call this a soluble salt. And then the hydroxide is what we call a strong base. So normally I would skip this step too because hydroxide hydrolyzes water completely. But what happens when it hydrolyzes water? So this is strong base. What happens is we form water and what's the other product of this? What's the other product of this? The other product of this is hydroxide. And so there's no change. And so usually you would skip this, skip, and then just go to the weak base. The weak base is acetate and water. This forms acetic acid and hydroxide. The hydroxide is going to change the pH. So the acetate we have is 0001249. Or no, is that the hydroxide? Actually, yeah, that's the hydroxide, sorry. Hydroxide is, so we have common ion. Hydroxide 0001249. molar. And then the acetate is what? 0.0499375. 0.0499375. So these come from the previous steps. So this is why it might be useful to do these steps here. But these are often skipped, especially by our book. And we go straight to this. I skipped it. I didn't do it completely. So this is going to be minus x. This is 0. This is plus x, plus x. So at equilibrium, we're going to have 0.0499375 plus x or minus x molar. I use molar here because your book uses moles. Your book is going to use millimoles, in fact, and what they have to do is they have to convert it back into molarity at the very end. And so they do the conversion step at the very end. I'm doing molar, so I don't have to convert it, but the numbers aren't so clean. They aren't as clean as your books. And so a lot of people prefer to use millimolar, which is fine. I don't care. But you could do all the variations you want, but you should just stick with one method that works, and then once you're comfortable with the one method that works, then start using all the other variations if you want, or just stick with the one method that works. People try to solve these using so many different methods, and they end up getting stuck. It's too much. It's just better for them just to stick with one. It's like, all the secret menus and stuff. You do all the secret menus and stuff, but once you're comfortable with the normal menu. X times 0.0001249 plus x over 0.0499375 minus x. I'd like to use the simplifying assumption for this, so we're going to just try it. For the simplifying assumption, I'm going to pick the smaller initial. So what I'm going to do is x is the same size in both. So I'm going to say x is much smaller than 0.0001249. And what that means is I'm going to get x times 0.0001249 divided by 0.0499375. And that means x will equal, didn't bring my other calculator. I don't like the new iPhone calculator. So we had, 5.55 times 10 to the minus 10. 5.55 times 10 to the minus 10 as our KB. Times 0.0499375 divided by 0.0001249. 3, 6, 7. I get an x of 2.219 times 10 to the minus 7. So first we'll check the percent change. And so that divided by 0.0001249 times 100. The percent change were okay. It comes out to 0.17. 7%. And so that looks good. So I'm going to go ahead and calculate the concentrations here because we're interested in the pOH. However, I want to calculate the remaining concentrations to double check my calculation. And so I'll do 0.0499375 plus 2.219 times 10 to the negative 7. And that gives me 0.0499377. So barely went up. Or it shouldn't have gone up. It should have gone down. Shoot. So it should be, it went up by 2. It should go down by 2. And so it should be 373. It barely went down. Okay, x, this is going to be 2.219 times 10 to the minus 7. And this is going to be 0.0001249 plus 2.219 times 10 to the minus 7. And this gives me 0.0001251. So it went up a little bit. Hydroxide. Will this perturb the previous step? No, this is not going to perturb the previous step. You know, adding a little bit of hydroxide here when we have a strong base in the prior step, this is not going to screw up this equilibrium. In fact, this equilibrium is nothing. Here. This is molar. So I'm going to do a check on my K and then C. So I'll take that times 2.219 times 10 to the negative 7 divided by 0.0499373. And I get this 5.559. Oh, it's off a little bit. Shoot. Times 10 to the minus 10. It's off a little. I didn't carry that many extra digits, so I would attribute this to round off. This comes out to 5.56. If we're off by much more than this, I would be worried I screwed up my calculation, but I'd say it's close enough. Okay. It's okay. Just take that. However, we're only allowed 2 sig figs in this anyway. So at 2 sig figs, it matches. But that doesn't say much because it's an artificial cutoff. All right, now our hydroxide that we ended up with is 10 to the minus 4. Are you going to worry about Kw? If I have 10 to the minus 4 hydroxide, no, not at all. Don't worry about it. And so let's go ahead and calculate the pOH next. So we don't have to worry about Kw. The pOH is just going to be the log of 0.0001251. 1251. I think 3.902. And then the pH is going to be 14 from that, 10.097. So within one drop, how much did the pH increase? Let's go back here. So we're at 872, and then within one drop, we're now at pH what? We're at pH 10 point. 10.097. 10.09. 10 point, no, we got to round up, 10.10. So we're at a 10.10 within one drop. So let's go to the next calculation here. I'm going to go well past the equivalence point. I'm going to go 10 milliliters past the equivalence point. And so we're going to do at equivalence point plus 10 milliliters. And so altogether that's going to be plus 30.00 milliliters of sodium hydroxide solution. Note that I do a new calculation for each pH. So for example, I don't start at the equivalence point and then just add from there. I start from the beginning. And the reason I start from the beginning is just easier. It's easier just to start it over. Calculation. So we'll just go ahead and we're going to do the step I, except this time we're adding 30.0 milliliters. And so altogether we're going to have a total of 50 milliliters of final volume here. And let's get the dilution factors. Okay, for acetic acid, dilution factor is we start off with 20, we end up at 50, so it's a 20 to 50 dilution, or 2/5 dilution. It's to 4 sig figs, so I'll just add on these. And the concentration is only to 3 sig figs. And so it's a 2/5 dilution. So I'll just do 2 divided by 5 times 0.1, 0.0400 to keep the, and then the sodium hydroxide is going to be a 30 to 50 dilution. So 30 to 50, 0.100 molar. So it's 3/5 dilution. I don't know what 3/5 is. 3 divided by 5 times 0.1. 0.06. Actually, these numbers come out pretty clean. When you have nice clean numbers like this, it makes the ice table a lot neater. And so we'll go on to step 1. K for this, as we said, is very, very large. Okay, so we'll have our initial change equilibrium. And so we have HAC at 0.0, was it 4? 4 and 6, yeah. 0.0400. And we have excess base, 0.0600. And this is 0. So acid's a limiting reagent, and this is going to take us to 0.0. It's nice to have these numbers here. It makes the math easier, 0.0400. So this is what we call a strong base, weak base mixture. However, because of the common ion effect, we can often ignore the weak base. No, weak base is often ignored. For 2 reasons. One reason is it's a weak base. The weak bases don't produce much hydroxide. The other reason is weak bases don't produce much hydroxide, and in the presence of common ion, they produce even less hydroxide. And so we just go straight here. We could go straight to the pOH. pH would be the log of 0.02. One thing I don't like about the new iPhone calculators, it doesn't have a clear key, all clear. You have to push the A. Oh, no, it does now. AC, I guess. 169, 8. And therefore the pH is 14 from that. 1230, 1. At a pH of 12.3, the strong base is dominant here. The weak base wouldn't have an impact, and for sure KW wouldn't have an impact. If you're ever uncertain, then go ahead and do step 2. Step 2 would be the weak base contributing, and then step 3, which would be KW contributing. Does that make sense? Okay. Which brings up, so once we go to 30 milliliters, we're already at a pH of 12.3. So let's go back over here. We go to 30 milliliters, we're at a 12.3 pH. At 12 milliliters. I mean, not 12, 30 milliliters. Okay, the next type of calculation is I want a pH of 11.00. How many milliliters will it take to get to a pH of 11? And so if I want a pH of 11 and I want to know how many milliliters, it's just all the same. We would start, and I prefer going forward here. So at pH 11.00, how many milliliters of sodium hydroxide will it take to get there? Oops, I didn't want to cross this out. It was by accident. It's all right. And so it's the same setup. You know, we do step I. Step I is 20.00 milliliters, except in this case, we're adding plus X milliliters of sodium hydroxide. And we have to know where we are in the titration. The one caveat to doing these kind of calculations is you must know where you are. Are you in the excess base? Are you in the buffer region? Because we handle the calculations differently depending on where we are in that region. And so we go to solution dilution. Solution dilution is going to be 20.0 plus X is my final volume here. And then I calculate the HAC initial. We're out of time, so I'm going to stop here and then do that. And then we just solve for X. That's it. So I'll stop here, and we'll continue this next time. We're actually almost done with chapter 19. I'm going to finish chapter 19 next week. Or 18. Is this 18? Sorry. We're almost done with chapter 18. So we're going to start chapter 19 next week, too. I'll post the homework. I'm going to, if somebody remind me, I'm going to post the quiz. You know, this week has been one day off, so I'm out of sync. I'm going to post the quiz for chapter 18 up. So why don't you work on that? I don't know. We'll figure it out next week. Probably the Monday after. Let's see. I should be able to finish this on Tuesday. Thanks, see ya.